Let's talk about recursion. I think recursion is one of those topics in computer programming where everyone at some point in their computer programming lifespan has or have been confused about it at some point. And then I think for many people, there's a point in time where it clicks. But I also think that one of the reasons recursion is so confusing is that a lot of the examples you'll find are kind of weird, frankly. Things like Fibonacci, factorial, and topics you just don't really run into on a day-to-day basis with computer programming. So today we're going to go into recursion with a practical example of why recursion is useful in some circumstances. I'm not saying you'll use it every day, but it's a nice tool to have in your toolbox. But first, I need to do a little silly example to explain one little base piece of knowledge that's needed to understand it. And to do that, I'm going to make a useless function that does something really useless, which is it takes in as input a single argument. It's supposed to be an integer. If that integer is greater than or equal to the number 3, then it will print all done. And so let's just test this and see if it works. And sure enough, when I pass in 3, it says all done. When I pass in 2, it says nothing. Okay, great. What would this function do if I were to, inside of this function, if n is not greater than or equal to 3, what if I were to call this function itself again, except pass in whatever I got for n plus 1? Now what would happen? So let's run this and see. You can see it says all done. Now why is that? And that is because this function has a recursive call right here. My function is calling itself, except it's calling itself with a slightly modified argument, whereas it was n the first time it was called and n was equal. So the first time through this function, n is equal to 2, this if condition fails because n is not greater than or equal to 3. So we fall to the else clause, and we then call my function with now the number 3, which means we then run again into my function, except this time n is greater than or equal to 3. We print all done, and this function returns. Now, where does it return to? It returns to the previous function call right here, my function, which then returns. Okay, so my function got called twice, once from here and once from inside itself. Now, I mean, this is a little bit weird, but to see it on the screen, let's just track that. So I'm going to say calling my function, and we'll just pass in the value n plus 1, and we'll just see this now on the screen. And let's just take a look, and we're going to run that exact same code with the extra print statement. And you'll see, okay, calling my function 3, all done. Now what happens if I pass in the number 0? Then you'll see more than one recursive call. So we're calling my function with 1, then with 2, then with 3, then that final function returns without calling itself. And where does it return to? It returns to this point from this place where it was called. You can see why this is confusing, right? And then, of course, that one returns here, and then that one returns here. And what's going on is that the Python runtime is keeping track of all of these function calls. And whereas normally if you were to look, for example, when you see an exception and you see a stack trace that shows all the different functions that were invoked and in what order, typically those all have different names. But in this case, it's actually the same function with the same name at the same line, except the Python runtime is keeping track of just exactly where and with what arguments it was called with. So there's your kind of weird, useless example to just walk through what recursion really is doing under the hood. And now let's look at an actual real-world example. So let's go with this little JSON file here. So this is like an employee directory where we have a single object in the root, which represents an employee whose name is Alice, who has ID number 1, and who has a list of employees that report to Alice. The first employee that reports to Alice is named Bob with ID number 2. Bob has no employees that report to Bob. Second employee is named Charles with ID 3, who also has no employees that report to Charles. And the third employee is named Elizabeth, who has ID of 4 and also no employees that report to Elizabeth. Okay, so let's say you were tasked with writing a function which can search this JSON file for an employee by name and then return the employee ID. So let's just call this function find employee. Sorry, I can't type. And you'll be expected to pass in an employee object, which represents one of these employees, to start the search at, and the name that you're looking for. So we're going to write this function recursively because it turns out, or actually, I'm sorry, no, we are not going to write it recursively. We are going to write this iteratively. What we are going to do is we're going to say, okay, if employee name is equal to the name we're looking for, then we should return that employee's ID number. Otherwise, we're going to go through the child employees in the employees. I know that's confusing. For each one of these children, we're going to search and we're going to say if this child employee's name is equal to the name we're looking for, then we will return that child employee's ID. Okay? So this seems pretty straightforward. Let's just write a little code to open this file. What do we call this? I think we called it simple.json as f. And then we're going to say employee equals json.loads f.read. And we do need to import JSON. And then we will call find employee. We will pass in the employee and we will be looking for Charles, let's say. And then we'll say Charles ID equals, and then we will print Charles ID. Except I need to type Charles correctly. Okay, let's run this little program. I'll just open up another terminal here. And we'll find that we have a syntax error, and that's because I forgot to do an opening paren. So we'll run this. I got another syntax error. I forgot a closing paren. And now let's run it again. Okay, so you can see this function, find employee, found Charles with ID 3. So great success. This program works just fine. But what if we have a more compile, or a much more complicated file that has multiple layers of nesting here? So it goes, I think, let's see. So we have one layer here, 2 layers here, a third layer here. So there are 4 layers of nested employees here. Well, what's one way we could solve this? One thing we could do is we could then, inside of this, we could say child employee in child employee employees, and we could repeat this same logic, except now, whoops, indented, and we'll just change that to that. That'll support 3 layers, and then if we want to support 4 layers, we would need to do this, and we'll just add child as a prefix here and here and here. Now we support 3 layers. And we could repeat this over and over again, but every time we do this, we're just pushing the limit down 1 layer. We're trying to solve a dynamic problem with static code. And this is a problem because we want to support files that have an arbitrary nesting in them. And you can see this is just not going to work with the approach that we're taking. So let's just throw all this away. And instead, recursive approach. You'll find, I think, that the recursive approach is actually a lot simpler. So let's switch over to our deeply nested file here. And this time we're going to search for Samantha because Samantha is deep in the tree here. Samantha. Okay. Now, if I run this right now, this should fail because, well, yeah, I haven't even implemented the function. But just to make sure everything's looking good, the ID comes back as none. So every time you're writing a recursive function, there is two parts. The first part is called the base case or the basis case. And this is where you inspect the data that was passed to the function and see if it meets the criteria that you're looking for. And if so, simply return it. This is like the trivial case where you have no nesting and you find the thing you're looking for right in the root. So it almost seems too trivial to write because why wouldn't the but you'll see in a moment that this is actually the beauty of recursion, is that this same logic will work at every layer when we come back to it. So we're just going to say if the root employee that was passed to us has the name we're looking for, then return that employee's ID. Of course, this will not work yet. We're going to return none because Samantha is not the name of the root Alice. But just to see if this actually would work, let's add a little print here. Find employee. We'll pass in the employee and we will pass in Alice. And we'll see if this prints out the number 1. Hopefully it will. And it does. Okay, so now we can see our base case is working. I'm going to delete that call. And now I'm going to say, all right, if the base case is not true, if the name we're looking for is not found at this root level, what if we reroute this same function call at the next layer in the tree? Well, it's not quite that simple because the next layer of the tree is actually a list. So we do need to iterate through the list of employees that belong to this employee, and we'll call each of those child employee. And then we just want to call find employee. Except this time we're passing in a new root and the same name. Now this isn't quite finished yet because all that's going to do is call recursively this function, and it will recurse all the way down through every single employee. But it's not returning the employee that it's going to find, because when we call find employee right here, we're not doing anything with the return value. So let's come back to that in a minute. But first, I just want to show what this is actually doing here. So I'm not going to show the name, the employee record, but I am just going to show, I am going to show the employee that's being called for, that's being searched, and the name name we're searching for. Now we'll get to see all the recursive calls, and there should be quite a few here. Let's just take a look. Look at that. Okay, so the second is that's what we passed in here. But the first argument, first we visit Alice. Look at this list with this list. We're diving right on down the list here. Because remember, in this for loop, the very first iteration through the for loop, we are calling find employee again. That this time with the first child, which means that this for loop will not execute further until the call to find employee finishes. So remember, we're going to stop execution here. We're going to jump back to the top of find employee. We're going to check the name, see if it matches or not. And if it doesn't, we're going to iterate through that employee's children. And so we go right down the tree, Charles, Darlene, and then we don't go any further. And then that first one returns, and then we hit Edward, then Fiona, then Samantha. And isn't that cool? I'm sorry, no, I said that wrong. Edward, Fiona, then Samantha. Isn't it cool how simply we were able to traverse all of these employee lists? There's 20 of them with just a few lines of code. So that is how you traverse a nested structure with recursion. But what about actually returning the value? Now this is complicated with recursion to think about mentally, because what's happening here is a whole nested set of function calls, one after the other. And you want to find the deeply rooted employee you're looking for and pass that back up to the calling function, which needs to pass it back up to its calling function, which needs to pass it back up to its calling function, all the way to the first calling function, which is this one, who can return it. How do we do that? Well, it's actually fairly straightforward to write, even though it's a little confusing to think about. We're going to say found here. And we're going to keep in mind that this function, if it does not find anything, it will return none. Like that. And if it does find something, you can see right here, we're returning the employee ID. But at the very end of the function here, we don't actually need to do this in Python. There's an implicit return none statement at the end of every Python function. But we're just going to put it here just to make sure. If we make it all the way through the child employee list and none of the children of that employee or their descendants returns a non-none value, then we're going to return none. So let me say that again. If we make it all the way through the list of child employees and none of them match what we're looking for and none of their descendants match what we're looking for, we will return none. So what that means is that this variable right here will contain none if we went all the way down that tree, came all the way back up, and didn't find it. But as soon as a single one of them comes back not none, that means we have found what we're looking for, and we can just return that ID. Or sorry, it is an ID, in fact. Let me just rename this because that's actually what it is. It's an ID number. And how do I know it's an ID number? Because this base case is the only place that returns an actual value that it found directly, as opposed to just passing a value that a recursive call found on its behalf. Okay, so that's recursion. Let's see if it works. Oh, I've still got my print statements, and we can see the path that it followed, and we got our ID number of 7. Let's scroll through our file here. Sure enough, there's Samantha with ID 7. So let's see what happened here. We went first to Alice. You can see here, that makes sense. Alice is at the root of our tree. Bob is Alice's first child, and Bob has children here. And the first child of Bob is Charles, and the first child of Charles is Darlene, which you can see here. But Darlene has no children. So in this case, we returned none after iterating through all 0 of Darlene's children. This for loop did nothing. Actually did have a child. Let's put one in here. And I'll just say, hello, as this person's name. ID doesn't really matter. I'll just say 444. And that is the only employee that Darlene has. Now we're going to see what happens to the tree. Oops. What did I do wrong? Key error. Oh, yes. My code assumes that everyone has an employees list, even if it's empty. Okay. Oh, did I do it wrong? Okay, there we go. So now we can see a slightly different path that it took. So we did Alice, Bob, Charles, Darlene, hello. Then we actually popped back up to Darlene. We didn't print it out though, because we already passed that point in the code. And then we went all the way back up to not Darlene's children, because we finished all the way down to Darlene. We went back to Charles's children, and you can see the next child under Charles is Edward. So you can see this recursion is so easy. It will go all the way down and up and back down neighboring branches as needed until it finds what it's looking for. And all that logic was done with just 2 cases, the base case and recursive case. Very, very simple code and a very elegant solution to this otherwise pretty complicated problem. So that's how recursion works. This is honestly one of the only cases I've seen where it's useful, is where you have a nested structure that has arbitrary depth and a tree-like shape to it. Other examples of recursion that you might have seen in the wild would be recursing through DOM nodes in an HTML tree. Very common in the browser to do that. I mean, not very common, but it's a commonly used use case that is appropriate for recursion. But there is one thing I want to call out about recursion that is quite problematic, which is there's actually a limit, a hard limit, to how much depth you can go inside of a recursive function. And to demonstrate this, I'm just going to make a single line function that all it does is call itself. Now you might be wondering, like, what's going to happen here? This looks like maybe an infinite loop, but this is not an infinite loop. This is indeed a stack overflow. Every single language that doesn't support tail recursion, which is something we won't talk about here, has a maximum limit to how many recursive calls can be made. In fact, not even recursive calls, but any number of function calls deep. Even if I had 10,000 functions, each calling each other one after the other in series, not one after each other, but rather one calling the next, there is also a limit to that, and that is called the maximum stack size, because your runtime uses a stack to keep track under the hood of all the function calls and where they are. And in this case, Python is telling us that we hit the max for that. And it'd be interesting to see what that max is, and passing in a 0, and then saying n plus 1 here, and just printing n. So what this does is we start at 0, the first function will be 0, and then the next one will come in as 1, and then 2, and so on until we blow off the top of our stack. So let's look here. Now we're going to have to scroll all the way back up to the very beginning of our call to see how big of a number we got to. 998, which means that on the 999th call, we blew the stack. And that 999th call was actually number 1000, which tells me that Python has a maximum stack depth or maximum recursion depth of 1000 calls. What that means is that if you're trying to traverse a structure, such as this employee list, or this more levels of depth, your algorithm will not work recursively. So that's one of the trade-offs you have to make with recursion. There is a risk that you will blow your stack, or I should say overflow the stack. And when that happens, you have no other option. You just have to fail. So it's great to validate that your data doesn't get too deep. So that's recursion. Hopefully that was helpful.